Now, one of the main mathematical tools that we need in addition to basic algebra is we need the ability to deal with things that are vectors. Now, you might ask, well, what is a vector? Well, a vector is a quantity that also has a direction associated with it. So at the end of the day, you could draw two arrows that are roughly the same length. However, it is possible to have them point in different directions, and thus we need a way to distinguish between the two. This is rather important because if you're trying to get from one location to another, you really want to be going in the correct direction. Now, when dealing with vectors, one thing to note is notation. There's two ways to represent if your quantity is a vector. The first is to have bolded text, so regular text in comparison to bolded text. And the other is to have a little arrow on top of your quantities. If you're reading print media, it is more traditional to use bolded text. But if you're writing it by hand, it's really, really hard to bold something with a pencil. So that's why the little arrow on top is also used. Now, these vectors actually consist of two parts, and those parts are actually quite literal. If you have a vector, let's call it vector B, it's made up of two individual parts. The first is its magnitude, or its overall length, which is a non-vector quantity, simply how long it is. If you go 5 meters to the left, the 5 meters part is the magnitude. And the second part is the direction. Now, typically speaking, we indicate a pure direction, which has a magnitude of 1 in all instances, by putting a little hat on top of whatever it is we're dealing with. This hat is referred to as a unit vector. Uh, the nice thing about this particular relationship here is it's algebraic. If you want to find the direction, or b with the little hat on it, you can simply divide vector b by its magnitude, normal b. Now, when it comes to representing these vectors, there's a couple of different ways to do it, and we'll talk about each one. However, one tool that you might be familiar with, which is specifically designed to help deal with vector quantities, is the Cartesian, or xy plane. You can extend this out to 3 dimensions, but we're going to deal with it just in 2 dimensions because that's the most common case you're going to run into. So you have an x-axis and a y-axis, and basically these two axes make a grid. And that grid is used to distinguish our vectors. So let's say that we have a vector indicated by this red arrow here, represented in 2 dimensions. Now, in 2 dimensions, in order to properly describe a vector, you need at least 2 pieces of information. The number of pieces of information you need must match the number of direction or dimensions that you're in. And again, these are not the unit dimensions. These are like left, right, up, down, forward, backwards. Now, if you want to represent this vector here, the first way that you can represent it is by using Cartesian notation. Cartesian notation, if you've ever played a little kid's game called Battleship, is basically that. What you're going to do is you're going to count how many units you've moved over, and you're going to count how many units you've moved upwards. So in this instance here, we'll use purple. You're going to move so many units to the right, and so many units upward to get to your final destination. And as long as your initial destination and final destination are the same, these two vectors are equivalent. So the purple path and the red path represent the same vector. Now what that means is if you want to represent vector A here, you can do so with 2 parts, the x part and the y part. And it's very common to write it in this form, x comma y. And this is the form that you're going to see me write it in most of the time. Now, with that being said, x is simply how far you've moved along the x-axis, and y is simply how far you moved along the y-axis. Now, it's important to note here that when you're doing this, you do need to keep track of the sign. So if we're going this way, our quantities are going to be positive, and if we're going upwards, our quantities are going to be positive. So to define vector A here using Cartesian notation, we're going to have a positive number for x and a positive number for y. The reason why I bring this up is because if your vector goes to the left, your x component is going to be negative, and likewise if your vector goes down, your y component is going to be negative. And this Cartesian notation here is one of the more common ways in which you can write a vector. What you'll see in the next section is in terms of algebra, This is by far the absolute easiest way to do it. All of our algebra, all of our math, our main goal is going to be to get our vectors into Cartesian notation, because there's no point in doing this and making our life harder than it needs to be. Now, with that being said, we can reset ourselves back to the start. There is a second way that is very common in representing a vector, and this is by using angular notation. And the main difference between this and, say, Cartesian notation is this angular notation is more intuitive for how people understand the world. The Cartesian notation is more mathematically useful. So let's consider this red vector again. Now, if you were going to walk from the origin or center of this Cartesian graph to where this red vector arrow lines up, typically speaking, you just walk right along the pathway to the end. This is basically what angular notation is representing. With angular notation, you're going to determine how far you're going to walk, which is r, or the magnitude of this vector, which is a scalar quantity. Right? So if it's 2 feet from the center of this graph to the end of the graph, or where the arrow terminates, r here would be whatever that distance is. Now, in addition, we need a second piece of information to indicate the direction. So we do this by utilizing an angle here from some particular reference direction, which we'll call theta here. What this means is, based on the reference that you've been given, you're going to rotate from that reference direction a certain number of degrees or a certain number of radians towards the direction you want to walk in, and then r is going to tell you how far you're going to walk. Now, there's a couple of different ways to represent this. You can use theta coordinates or whatever else you want. However, the most common way to represent this entire vector, which we'll call vector r here, is to say that this vector is equal to the magnitude, or how long the vector is, how far you're going to walk, multiplied by the direction. Now, for this direction, we're going to put it into square brackets, and we're going to start with the first direction, or the one that our angle is coming out from. So here, if you look at how we've drawn this angle with the little angle arrow, it starts at the x-axis, or pointing to the right, and is rotated towards the next axis, which is the positive y-axis, or the upward axis. So what we do is we'd say this is right. You can even use an arrow if you want. You can call it, east if you want. It really doesn't make a difference so long as you've indicated clearly what the reference direction is. We're going to follow it up by saying how far we've rotated from that reference direction. And then lastly, we're going to put the upwards arrow here to terminate our direction. So we're starting from the right. We're rotating so many degrees towards the upward direction. And that's one of the most common ways of writing a vector in this particular direction. This one is a little more specific, or a little more explicit to the definition of a vector, because we have a magnitude and a direction.